So thanks, Dean Moffat, for the nice introduction, and hello, fellow retrievers. Okay, so when we move away from our world of everyday human experiences, things like tables and chairs or apples falling from trees, and we go down to the scale of some of the smallest building blocks in the universe, things like atoms, or even smaller particles like photons and electrons, what we find is that the laws of classical physics, that is kind of regular physics, like many of you learned in Physics 101 right here on campus, those classical laws start to break down and the laws of quantum physics kick in. Now, the laws of quantum physics are wonderful. They always get the right answer. We've tested them thousands of times in thousands of different ways, and we know they're correct. The tricky thing is, the foundations that these quantum physics laws are built upon are very counterintuitive. They're unlike anything we see in our everyday human experience, and quite frankly, they're kind of strange. And so I think this sentiment is summed up very nicely in a series of quotes, my favorite being the one by Niels Bohr, where he says, if quantum physics hasn't profoundly shocked you, you haven't understood it yet. For what we see in quantum physics is behavior like inherent randomness in the universe. We see particles being in two places at one time, and even quantum entanglement, or connections between distant particles that Albert Einstein once described as spooky action at a distance. So, whoa. When we think about these things, the kinds of questions we're going to be asking are along the lines of, does the moon only exist when I look at it? Now, obviously, at this large human size scale type of system, the answer is yes. But when we get down to the quantum realm, we have to take very seriously the analogous question of, do the properties of a quantum system exist only when I measure them? And so here we're talking about things like the spin of an electron, the energy of an atom, the color of a photon, or even something as simple as the position of a tiny little particle. And so to unpack this a little bit more, let's look at that last example, the position of a particle. And what we find is, in classical physics, the position of a particle is completely well-defined. If I put my particle over here, my particle is at that location. In contrast, in quantum physics, our particles are described by wave functions, these wiggly, wild things that kind of spread out in all space in such a way that the position of the particle isn't really defined. In fact, it's as if the particle is at all locations at the same time. Now, when I go to measure the particle, if I reach my hand in and try and find where it is, I make a measurement, something very interesting happens. This wave function kind of collapses down to a very well-defined but randomly located point. And so now the position exists. Okay, these two red items here are very serious when we think about science. On the first point, random outcomes, Albert Einstein gives us his famous quote of, "God does not play dice with the universe." But even more seriously is the other issue. For Einstein and many others like him at the time of the development of quantum mechanics, the idea was that there had to be an objective reality out there independent of the observer. The position had to exist whether I measured it or not. And so to poke at this a little further, Einstein and some of his colleagues said, hey, let's look at not just one particle, but let's extend up to two particles. Okay? And if this quantum mechanics stuff is all right, then it allows these particles to be entangled in such a way that they share a joint wave function that looks like the video going on in the background. And what quantum physics would predict in this scenario is, if I make a measurement on this particle over here, its wave function collapses and I find the particle at a random location. It's very strange, but we've seen it before. Remarkably, at the same time, the wave function of the particle over here also collapses to a random location. Now, the correlations between these random locations are quite interesting, and in fact, they're necessary to understand all the subtleties of what's going on here. But the key message here is that a measurement I performed over here causes something to happen over there. And in the summary of Einstein's paper, he says, no reasonable definition of reality could be expected to permit this. Something probably many of you are thinking right now. The situation gets even stranger when we consider that quantum mechanics doesn't care about the distance between the particles, and so this can happen over very large size scales. Okay, so Einstein and his colleagues bring up this issue of quantum entanglement in 1935, and it took roughly 40 years of scientific advances and developments before entanglement was experimentally verified in the laboratory. It took another 40 years until I think this idea was widely accepted by the scientific community, in fact, and recognized by a Nobel Prize just 2 years ago in 2022. Now, in the meantime, there was something very exciting going on behind the scenes in the 1980s and 1990s. People were moving on from the ideas of just studying entanglement or seeing if it exists to asking, can we actually use quantum entanglement and these quantum effects, kind of bring them up to a human scale level and do something useful with them? And the answer was a resounding yes. It turns out we can process information using quantum effects in very new and powerful ways. And so that brings us to where we are now, which can only be described as a quantum information processing revolution. We've seen tremendous growth in the ideas and developments behind building things like quantum computers, quantum communication systems, quantum sensing devices, and a whole host of other quantum technologies. And this field's exploding in crazy ways by any metric you can think of. We see this in the number of patents, which has just skyrocketed in the last 10 years in the field of quantum information. We see this in tens of billions of dollars being invested by governments around the world for quantum information research. We see incredible hype like Time Magazine, my talk right here, and other things. But importantly, what we're seeing is a renewed interest in science by young people. It's also led to the development of a very large number of companies investing in quantum computing. Not only some of the heavy hitters that you see there, but also something on the order of 300 small startup quantum information companies around the world as we speak. Okay, so I want to wrap up here by saying that, and emphasizing that, a lot of pioneering research in quantum information has been done and is being done right here at UMBC. In fact, we're in the process of setting up a brand new quantum science institute, which is going to bring together faculty and students from several different departments across campus. And it's not only going to enable us to collaborate and accelerate our research and make more breakthroughs, but it's going to enable us to offer cross-disciplinary quantum science courses and academic tracks that are going to help to prepare, to train and educate our students to become the next generation of a quantum-ready workforce. So with that, I'll close. It's an exciting time for quantum physics, and it's an exciting time right here at UMBC. Thanks for your attention.